Kind of a throwback to grade 11 waves and sound. If we know the wavelength of a wave and the speed that it's traveling at, we can use the wave equation to find the frequency. Basically, if we know any two, we can find the third. The wavelength of orange light, each slightly different shade of orange would have a slightly different wavelength. I just made up a nice clean number. 600 nanometers is orange. Nanometers means 10 to the negative 9, a billionth. So it's not that 600 times 10 to the negative 9, or kind of a better form, 600 is 10 to the positive 2. That combined with a negative 9, we could call that 6 times 10 to the negative 7. Just plugging in the values, the speed of light in air or a vacuum is 3 times 10 to the 8 meters per second. I don't know the frequency. The wavelength of orange is a 6 times 10 to the negative 7 number. So we take our meters per second, we divide by that number in meters. We're going to get a number that's in per seconds. The value works out to be 5 times 10 to the 14, and per second we call those hertz. So if we were to create orange light by shaking a charged object up and down, like maybe you grab an electron and shook the electron like a crazy person, if you could shake that electron up and down 5 times 10 to the 14 times per second, that would create ripples in the electric and magnetic field that would propagate outward. When those ripples hit our eyeball would decode that as a shade of orange. The amplitude of the vibration would be the brightness of the wave, but the frequency, which is connected to the wavelength, those two would tell you the color that we would see. Light, we picture it as this electromagnetic wave, so it's got two components, the electrical component vibrating in one way, the magnetic component vibrating perpendicular to that, and then the energy sort of perpendicular to both of those radiating outward.